So, what did we do last time? We talked about Coulomb's law, electric charge, why this course is important, why it almost explains everything we see around us except for the gravitational force. And the last thing we did was a quiz. So let's see how we're going to solve this quiz question. I have two charges, Q1, 1 Coulomb, and Q2, 0.75 Coulomb. And their positions are given. Q1 is at the origin, and Q2 is at 1 centimeter x and 1 centimeter y. Find where a charge Q3 should be placed so that the second charge Q2 is in equilibrium. So what do I want? What does that mean? Charge Q2 is in equilibrium. Net force on Q2 should be exactly 0, right? Now, the first thing we learned about Coulomb's law is if I have two charges, Q1 and Q2, the force acts on the line that's connecting these two charges, right? Now, Q1 is positive, Q2 is positive. What's the force? What's the direction of the force Q1 is applying on Q2? It's exactly on the diagonal, right? So this is going to be F. First charge is acting on the second charge, right? So what do I need? I need a force which is going to cancel this force exactly. Now, F3 acting on 2 should cancel F1 acting on 2 exactly. So I know the direction of the force. So where should I place Q3? I can immediately say that I have to place it somewhere on this y equals x line. Why? Because if I put it any other place, there will be a component of the force which is not on this line, which will not cancel F12, right? So Q3 is negative, Q2 is positive. So they are repulsing or attracting? They are attracting. So should I put Q3 to the left of Q2 or to the right of Q2? To the left, so that it actually attracts Q2. So I want Q3. I reason that Q3 should be somewhere here. Now, let me call this distance d. How about the distance between Q1 and Q2? It's square root of 2 centimeters. But let me call it r. All right? R is square root of 2 centimeters. Now, let me write the magnitude of F12. The magnitude of F12 is 1 over 4 pi epsilon 0 Q1 Q2 divided by R square. How about the magnitude of F32? 1 over 4 pi epsilon 0 Q3 magnitude Q2 divided by R plus D squared, right? And I know that these two must cancel exactly, so F12 magnitude must equal F32 magnitude. Let's write everything. 4 pi epsilon 0 Q1 Q2 divided by R square is 1 over 4 pi epsilon 0 Q3 magnitude Q2 divided plus 1 over 4 pi epsilon 0's cancelled. Q2's cancelled. Now I can put in the numbers. Q1 is 1 coulomb divided by R square. Q3 is 0.75 coulombs R plus. Q3, let's see. Q3 is minus 4, so this should be 4 coulombs. Excellent, thank you. So what do I find? R plus D over R is square root of 4, which is 2, which means D is R. Okay, did I solve the problem? Well, I kind of did solve the problem, but I did not state my answer the way the question asks. And that's an important part of being a scientist or engineer. Whatever is asked in the question should be replied the way it's asked. So what does the question ask me? It asks me to state the x and y coordinates of Q3. So if D is equal to R, can you tell me the x coordinate of Q3? It should be minus 1 centimeters. Do not forget your units. Okay? How about y of Q3? It's again minus 1 centimeters. Can I see a show of hands how many of you actually found this result minus 1 and minus 1? Well, that's great. Did you write your units? Minus 1 centimeters? So, okay, so you'll miss some points if you didn't write that. Be careful. Be careful with your units. Now, here is one simple question. What would change if Q2 was, say, minus 5 coulombs? I'm going to go through the same problem with Q2 equals minus 5 coulombs. Would anything change in my solution? Nothing will change. Why? Because whenever I actually talk about these two forces being equivalent, Q2 cancels. It doesn't matter whether it's negative, whether it's positive, whether it's 5 coulombs, 1000 coulombs, or 0.1 coulombs. So maybe I can actually use this to my advantage. Okay? In many problems, it wouldn't matter what the exact value of the charge I am putting into some space point. Okay? So I'll actually make a new definition. I'll define the electric field. I'll say if I have a charge Q that's seeing an electrical force F, it's seeing this electrical force because there is actually an electric field E at that point in space. So I can actually define the electric field as F divided by Q, which means, quite simply, what is the dimension for the electric field? What's the unit for electric field? Apparently, it's newtons per coulomb. Okay. Now, this may look like a mathematical trick, right? I'm saying I don't really want to calculate the force between two pairs of charges. I'll calculate something called the electric field, so I can actually quickly calculate the force for any given charge at that point. All right? But it's actually conceptually very different. When I first wrote Coulomb's law, I said there is a charge Q1 here and a charge Q2 here, and my Coulomb's law told me that there is a force F which is a constant times Q1, Q2 divided by R square. Now when I write something like this, it assumes that these two charges know about each other, right? And they know about each other from afar. If I quickly moved Q1 away, would the force on Q2 change? If this formula is correct, it must immediately change. If the distance between these two objects is changing, the force must also change. So such formulas, including Newton's law of gravitation, are called action at a distance formulas. And although Newton wrote the first such formula, he was not very happy with it. He said, how come does the Earth know about the sun's position immediately? A lot of people actually at the time criticized Newton for writing such a formula. They said, information, well, they didn't exactly say that, but this effect must travel in space in some way. And here we're actually, by defining the electric field, we're actually making a philosophical jump. I'm saying, hey, here's Q1. Even if there is no Q2, it actually changes something in the vacuum. Even in the absence of the charges, just a single charge in space creates what we call a field. What's a field? A field is a vector at each space point. Now, if I actually move this charge, the electric field will be affected, and towards the end of the course, we'll see that we can write how it is affected a little bit better than action at a distance. We can actually see how fast electric field learns about the motion of the charge. But right now, we're making a philosophical leap. We're saying, hey, even if there are no charges around, a single charge in space creates a new field at each point in space. Now, if I put Q2 here, Q2 does feel the same force. But it's not because it feels Q1 from afar. It locally, at that point, feels the electric field. Right? Now, the distinction you may think it's academic, but it's actually very important. The way I write electric field, it looks like a mathematical trick. The question is the electric field real? Now, would you say that an electron is a real object? No? You don't think electron is real? It's not an object? No, the electron can be by itself. So, okay. So we're going back to philosophy, so it's not going to be like physics. Is this pen a physical object? Why do you say this is a physical object? It has some mass, but I would say it actually has two more things which make you feel it. One of them is that it can carry momentum. It can hit my hand. I'll feel that. And it can have some kinetic energy. If I throw it, it's an expensive pen. I'm not going to throw it away. Okay. If I throw it, I'll actually give it some kinetic energy. It can carry momentum. It can carry energy. And if I rotate it, it can also carry angular momentum. So it turns out, and this is quite interesting, electric field, we'll see, can store and carry energy, momentum, angular momentum. So it turns out, although I'm introducing it as a mathematical tool, I found a new physical object, the electric field. The electric field is as real as the pen in my hand. Okay. You may say, hey, I know your pen is made up of atoms which have nuclei and electrons, so what is the electric field made up of? Are there constituent particles? The answer to that comes from quantum field theory. Yes, there are constituent particles which we call photons, which are as real as atoms. Now, let's just put this philosophical discussion aside. How does this help us? Okay. It helps us in the following way. Instead of talking about pairs of particles, now I can think of a single particle and its electric field. If I have a particle Q at the origin of my coordinates, not even Q1, I'll make it Q, X, Y, Z, the electric field at any point X, Y, Z this will be the radius vector, this will be the unit radius vector. The electric field at that point is going to be 1 over 4 pi epsilon 0 Q divided by R square, or if I write R in terms of X, Y, and Z, let's stop immediately. I made a big mistake. I did it intentionally. What's wrong with these two formulas?
The direction of the electric field is not shown in the...
Exactly. Electric field is a vector. Okay. So I have to, when I write an equation, I must make sure if the left-hand side is a vector, the right-hand side should also be a vector. The way I wrote these, the right-hand side is just a number. What do we call numbers in physics? Okay, so we could just keep calling them numbers, but we want to impress our grandmothers, right? If you went to your grandmother today, you said we worked with numbers, she will not be impressed. If you tell her we worked with scalars today, she would be impressed because she doesn't know the word, right? So this is the scalar part, and this is the direction. So this whole thing becomes a vector, and this is a vector. Now, what do we, yes?
Is the distance in the second formula, is it correct?
No, it's not correct. That's very good. That's the second mistake. That is the correct formula. Thank you. I hope I'm getting all of you to pay attention to what I'm writing down. Now, question. What's a field? Can anyone define what a field is? Any math majors here? Okay, that's very good, because math majors would give you a long definition of a field. In this course, as long as this course is concerned, a field is something very simple. E of x, y, z is a vector at each space point. So Visualizing it is somewhat hard, right? For a simple charge, it's easy, okay. I know what the electric field looks like. I can put a vector at each point in space. But think of this three-dimensionally, so it's like a hedgehog. You know what a hedgehog is in Turkish? Kirpi, so it's like arrows pointing out all the time. And if I go far away, I'll have smaller arrows. And if I go very close, I'll have very big arrows. And you see that the arrows start overlapping with each other. So maybe this is not the best way to visualize the electric field. All right. So people did come up with other methods of visualizing the electric field. And let's talk about one of them. Let's talk about electric field lines. And these are going to be much, much easier. Why? Because they are constructed with very simple rules. If I have a plus Q here, here are the electric field lines. They are just going from plus Q to infinity. And here are my rules for constructing field lines. The first rule is electric field lines start on positive charges or at infinity. They end up on negative charges or at infinity. The second rule is electric field at any point is tangent to the lines. And the third rule is electric field magnitude is proportional to the density of field lines. Now, why are these good? They are good just because they are easy to draw and they give you some intuition about what the electric field of an object looks like. Okay. Let's do the following. Let's take a plus Q charge and a minus Q charge and try to draw the field lines, electric field lines between these two objects. So what are my rules? My rules, the first rule is any line must start either from a positive charge or must come from infinity. Now here I have plus Q, so let's say I have a line going right. At each point, the line, the tangent to the line must be in the direction of the electric field. On the line connecting plus and minus charge, electric field is always linear to that line. So the first line must be connecting plus charge to the minus charge. What happens if I have a field line leaving this perpendicularly? Well, electric field will start bending towards the negative charge, right? So what will happen? This line would actually bend, and it will end up on the minus charge. I could just as well write another one. And here comes the utility of electric field lines. If you think about it, electric field at any point is tangent to the lines. That also means something else. The field lines do not cross. Why? Because if I had a crossing, I would have two tangents at that point, right? Tangent along one, tangent along two. But I know that electric field, a field is a vector at each point. It's not two vectors at each space point. All right? So field lines do not cross, which means if I actually draw two lines, I can pretty much just fill in between them without crossing. How about the line that's actually going exactly to the opposite of minus q? What will happen to that? It must always stay tangent to the electric field. So it will actually go all the way to infinity, which you can say is coming back from infinity to minus q. So you can fill in all these field lines. Now, why is this useful? It's sort of, by just drawing lines, it sort of tells me, if I'm wondering what the electric field somewhere here is, it pretty much tells me that it must be to the right. If I'm wondering the direction of the field somewhere around here, these field lines are very good ways to think about what the electric field looks like. But, so that gives you intuition. It's sort of, it will, especially for the electrical engineers here, when you think about electromagnetism, when you take courses on electromagnetism, you'll have to do design. You'll have to design a new antenna. You'll have to design a new receiver, right? Then you need some intuition. You need to understand how charges move, what kind of electric fields they create. So it's easier to think in terms of these field lines. However, they will not help you calculate anything. No engineer actually goes ahead and draws field lines anymore. Right? So we actually have to do something better. We actually have to calculate the electric field for any given arrangement of charges. Okay. So how do I calculate the electric field of a collection of charges? Now I'll actually stick with the same example. Let's say this is my x equals 0 point. I'll put a charge minus q, or let's say this is plus q here, at d over 2. And I'll put a charge minus q, another distance d over 2 here. And I'm wondering the following. What is the magnitude of the electric field as a function of x, underline x? So let's make this an exercise. Now, this is pretty simple, right? If I have more than 1 point charge, how do I find the total electric field? I just find the electric field of both charges and do a vector addition, right? So here is what I would write. Electric field has two components. First, I'll have the electric field created by plus Q. So I'll have this E plus. And then I'll have the electric field created by minus Q, E minus. So the net electric field will be E plus plus E minus, right? Or, because they are in the opposite direction, E magnitude will be E plus magnitude minus E minus magnitude. Okay. So, which way will the electric field be? To the right or to the left? Come on. How many of you say it's to the right? How many of you say it's to the left? Why are half of the class abstaining from giving any opinion? Come on. How many of you say it's to the right? Okay, that's much better. Why is it to the right? Because positive charge is closer to the observation point, right? So it creates a higher electric field. E plus must be larger than E minus. Now, what's the magnitude of E plus? Well, 1 over 4 pi epsilon 0 Q divided by, if the distance here is x, the distance between plus charge and the observation point is x minus d over 2. How about E minus? 1 over 4 pi epsilon 0. Because I'm taking the absolute value, it's Q again. Now this is going to be x plus d over 2 square. So you can say E magnitude as a function of x is 1 over 4 pi epsilon 0. I can even write it as Q over 4 pi epsilon 0. 1 over x minus d over 2 squared minus 1 over x plus d over 2 squared. Okay. Now, that's the full and correct answer. However, this arrangement, a plus q and a minus q, that is separated by d, it gets a special name. This whole object is called a dipole. Now, why would an arrangement of two charges get a special name? The thing is, a lot of physical systems are electrically neutral. Think of the hydrogen atom. What are the constituents of the hydrogen atom? An electron and a proton, right? One of them is charged with plus charge. The other is cancelling its charge. It's exactly minus. But are they exactly on top of each other? No, the electron is, if you want, rotating around the proton. So there is a distance between them. Do you know what's the typical distance between the electron and the proton in the hydrogen atom? It's about 1 angstrom. Angstrom is 10 to minus 10 meters. So think of the hydrogen atom. I have a plus Q charge and the minus q charge, and the distance between them is 10 to minus 10 meters. So here is my question. If I am 1 centimeter away from the hydrogen atom, do I feel an electric field or not? Is there an electric field or not? There is an electric field. We've just calculated it, right? However, maybe I don't really need to talk about all this detail. Maybe there is a simpler formula. I can approximate it to a simpler formula. Because the distance of my dipole, d, is much, much smaller than the distance from the dipole to the observation point. So can I approximate this formula and get a better answer for the dipole electric field? And that's what I'll do. Now, let me write this formula in a different way. E of x is q over 4 pi epsilon 0. I'll take 1 over x squared out and write this as 1 over 1 minus d over 2x squared minus 1 over 1 plus d over 2x squared. Now comes the nice and magic part. Do you remember the binomial expansion formula? How it starts? It starts as 1 plus n times epsilon plus n choose 2 times epsilon square. Right? It goes on like this. Now, if epsilon is much, much less than 1, for example, let's say epsilon is 0.0001, which term is more important, epsilon term or epsilon square term? Epsilon square and all the rest are extremely small. So if I have a very small number, 1 plus epsilon to the n is almost 1 plus n epsilon. I know you don't believe me, so I'm going to call up a calculator here. Really, I'll do that. I would want you to calculate 1 plus 0.0001 to the 5th power, and it should be almost 1 plus 0.0005. Okay? Check it with your cell phones right now. Really do that. Take this to the 5th power or square power and see that it works. Now, what does this tell me in terms of my formula? I said E of x absolute value is q over 4 pi epsilon 0 x squared. Now, 1 over 1 minus something very small square is actually 1 minus something very small to the minus 2 power, right? So it should approximately be 1 minus 2 times minus d over 2x. And here I have 1 minus 2 times d over 2x. Twos cancel. Ones cancel. I have q over 4 pi epsilon 0 x squared d over x plus d over x, which, let me write it down, q times d divided by 1 over 2 epsilon 0 x cube. So this is kind of interesting. If I have a dipole, if I have this hydrogen atom, and I'm going away from the hydrogen atom, I still see an electric field. But this electric field is not decaying as 1 over x squared with the distance, but it's decaying with 1 over x cube with the distance if I am far away enough. Okay? And because q times d comes up all the time, it's given a new name. Q times d is called P, the dipole moment of the system. So electric field of a dipole is P over 2 pi epsilon 0 x cube. But now be careful, I just calculated it on the line of the dipole moment. Okay? Its behavior will be a little bit different if I go perpendicular to the line of the dipole. Okay? That's something else for you to calculate. Right? Good. So let's maybe stop, and the first thing we're going to do next lecture is the quiz. Right? So come back here promptly at 40 past the hour.